Hey, hello all. In this lecture, I'll be going over the basics of genetic algorithms, what they are and how they are used. Genetic algorithms is a powerful optimization technique inspired by the process of evolution and natural selection. Genetic algorithms are particularly useful in solving complex optimization problems in the field of AI, for example, where traditional optimization methods may struggle. In this video, I'll give you an overview of what the algorithm is, its various parts, go over some steps of how to construct a genetic algorithm, and finally, we'll go over a small real-life example which will allow you to get a sense of how to use this idea of natural selection more mathematically, how to code it. So let's dive in. A genetic algorithm is a search heuristic that uses principles of evolution. In other words, we have an optimization problem at hand and a search space that contains all possible solutions. Any optimization algorithm tries to effectively explore the search space and find an optimal solution. In the case of genetic algorithms, it uses the fundamentals of evolution such as selection, crossover, and mutation to explore this space and search for the optimal solution. In this algorithm, we work with a population of candidate solutions called individuals. Each individual represents a possible solution to the problem. The algorithm iteratively evolves the population towards an optimal solution through a series of steps. Let's take a closer look at some of the major steps involved. First, obviously, we have to initialize the population. So, we create an initial population of randomly generated individuals. Even though this is a random process, we want the population to contain various kinds of individuals or solutions. In other words, we want diversity in our population. Next step is to find a way to evaluate each solution. You assign a fitness score to each individual based on how well it solves the problem. Next is selection, where we choose parents for reproduction based on their fitness scores, with fitter individuals having a higher probability of being selected. Once these parents are chosen, we create offsprings by combining genes from the selected parents. Next is a very important step while generating offsprings, which is adding mutation. While mutating, we introduce small random changes in the offspring's genes to maintain diversity within the population. In a more mathematical sense, this helps us explore the search space in newer directions. You see, any approach to solving a complex optimization problem has to strike a balance between exploring and exploiting. Exploring is about trying something new, whereas exploiting is about doubling down on things that you know work. So when we choose parents that are fit and take their genes or their solution, we are exploiting what we already know. Mutation allows us to try new things, which may work out even better, which is all about exploring. From a search space perspective, it helps us look in different directions, which will prevent us from getting stuck in some local optima. Also, if there is no mutation, any offspring in any generation will just be some combination of the individuals of the original randomly chosen population, right? It'll just be a combination of those original folks that we chose, which is very limiting. Finally, we replace the old population with the new offsprings, and we do this repeatedly generation after generation. We keep repeating these steps until a termination condition is met. Either we found an optimal solution, or if the overall population is not getting any better generation after generation. That really depends on the type of problem you're trying to solve. Now that we have covered the basic steps, let's go over a small problem statement through which one can get a sense of how to code this thing. Let's say we want to use a genetic algorithm to solve the traveling salesman problem, a classic computer science problem. In TSP, we have a list of cities and the distances between each pair of cities. The goal is to find the shortest possible route that visits each city exactly once and returns to the starting city. For those who are not familiar with this problem, this may seem like a trivial problem at first, but the number of potential solutions grows exponentially. And it's not feasible to check all solutions beyond let's say, a small number of cities. We start by identifying how to encode each solution. We can represent each individual as a permutation of city indices. For example, if we have 5 cities, an individual might be represented as 31425, which represents a certain route, a certain solution, which starts at city 3, goes to 1, you go to 4, then 2, then 5, and then back to 3. So that's one solution, one individual. Then we define a fitness function. We try to evaluate each solution or individual by defining a fitness function. In this case, it is a little bit obvious. The fitness function will be the inverse of the total distance traveled in the route, in any route. Since we want to minimize the total distance, a lower distance will obviously yield a higher fitness score. We move on to selection. We can use something like a tournament selection, where we choose a small subset of individuals from the population and select the fittest individual from that subset as a parent. Once we have chosen fit parents, we move to crossover, where we try to take the best of both, or at least elements from both, to produce an offspring. There are many ways to do this crossover operation. It also depends on the problem at hand again. Here, we can use the ordered crossover, the OX operator. Given 2 parents, OX selects a random subsequence from one parent and fills the remaining genes in the offspring by following the order in the other parent. Let's take an example to understand how this crossover works with numbers and why it makes sense. Imagine we chose 2 parents, P1 and P2 as shown. Let's try to produce one offspring from these parents. As you see, a random subsequence has been chosen. Suppose we take 271 from the first parent. That gets copied as it is to the offspring. Now, we move to parent 2 for the remaining genes, or the remaining cities in this particular example. We start filling in from the second cut point, and the bits from the other parents are copied in the same order, omitting existing bits. So, the sequence of bits in the second parent from the second cut point is 3742568, right? And since you can't have 271, we skip those bits. After removing and omitting those bits, the new sequence becomes 34568. This sequence is placed in the first offspring, starting from the second cut point to produce the final offspring. Why did I say first offspring? It's called O subscript 1 because you could also do the reverse, choosing the middle 3 elements from the second parent instead of the first parent as we did, and the rest from the first parent instead of the second parent. Or this will lead to another offspring. Anyway, this is just an example to demonstrate a method of crossing over. It's used in problems like TSP. Once you have an offspring, you want to add some mutation. We can use the swap mutation in this case, where 2 random genes within an individual are swapped with one another. This mutation operator ensures that the offspring remains a valid permutation of city indices, as any mutation criteria would have had to. In this case, we can set a maximum number of generation as the termination condition, right? So you run the loop a certain number of times, and when the algorithm reaches its limit, it returns the best solution it has found so far. So that's it. That's a brief overview of genetic algorithms and how they can be applied to solve a problem like TSP. While this example focused on a specific optimization problem, genetic algorithms can be applied to a wide range of problems in AI. With a solid understanding of genetic algorithms, you'll be well equipped to tackle various optimization challenges, like the one coming up very soon. Following this small lecture, I've added some notes, some common selection, crossover, and mutation methods, various methods, which should add to your sense of genetic algorithms. and help you find your own methods given any specific optimization problem.